Okay, so we were talking about sequence models, and we went on to say that there is this simplified tasks with just repeating one digits, and we managed to find one way to train the model to really work, meaning work 100% on this task. It looks like I don't have Wi-Fi down here, so. But anyway, this is an hour for you to work. So let's try to think about solutions for this positioning problem. Right? We had the problem that to solve this task, the convolution, well, it needs to take this position, the identical position when it's even, and the position one to the left when it's odd. And if it doesn't know what position it's in, then it is not able to do it. If it knows what position it's on, for example, because we had learnable vectors for all the 10 positions, then it works. But it's very unsatisfactory to have just learned vectors for 10 positions, because we want an algorithm, we want something that will work for 12 positions as well later, while this obviously will not, because it just has 10 of these vectors. So how can we solve this problem? And how can we handle variable length sequences then? That's a question for this exercise. So I hope you can come up with some solutions. I can suggest some, and then should try them out in the Colab and make them work. So what solutions would you propose? We can encode. What can we encode? Pairs?
Yeah.
Pairs of?
Yeah, instead of 10, then we would have 5. Then we have 5 characters, and you could just code to digits. And then you would always need to somehow take the pair, extract first, and repeat it twice.
A pair of?
2 consecutive digits.
Oh, so we could change the data on input to make the problem easier. Yes, but we want a solution that, in the end, we want a network that works on other problems too. Right? This is the pattern in deep learning. You want a network that you will be able to apply to many problems. So yeah, this would solve it for this thing, but we would have a different problem. And then we would need triples, quadruples. It wouldn't work universally.
The simplest thing would be to have a mask with bits matching the bit that we would like to replicate.
Well, but this is, again, something designed for this problem.
Use recurrent neural network and add concatenated vector with a position. So, for instance, we would add concatenate vector with 1 is even or 0 is odd.
So again, we would have.
Recurrent neural network.
Mm-hmm.
And
it would.
during training stage, we concatenate the value of the digit and concatenate with its parity.
But if we concatenate it with its parity, then we've devised a solution for this exact problem. We know how to solve this problem. We made it, right? The Python generator solves it. The point is to make a model that would solve this and other problems. So we would really want a model that doesn't know about parity, right? Parity is a property of this data set. And we want a model that doesn't know about parity, but it learns to solve it, right? This is the thing in deep learning, right? You want one model that solves many different tasks. If you give it parity, then it will solve well tasks that are related to parity. But what if it was modulo 3?
Just give it the position.
Mm-hmm.
Just give it the position.
Just give it the position. Okay, so positions, so this is our sequence. And the positions are 1, 2, 3, 4, 5, 6. So what does it mean to just give it a position? Yes, so we have tuples, so this is like 0, 5, right? This is 1, 6. But the question is, how do we represent this position as a vector of floats, right? Because one thing is to learn an embedding, a different vector for every float. That's what we did. Where did we do this? We did it right here, right? This is the positions variable. It has a separate vector for every position. The only problem is that maybe at training time we only see 6 positions, but at testing time we will have a 7th, which we've never seen on training. Sorry. So how can we make sure it generalizes to this case?
Can we work on streams? So have an input stream and then like create an output stream with the same value. Is it okay? I mean, for this kind of
Tensors, streams look similar.
So if we learn this network on a stream which has only 10 values, it can generalize on other streams. So we are just like taking one digit after digit, and then we can learn it.
Okay, so you want to say we would have something like an automaton that, so instead of this learned position vector, it would just generate like the next position vector from the previous one, something like that. Well, if it generates the next, then it certainly generalizes to more next, right? Okay, so that's one idea. So instead of having learned embedding for every position, we have something that, given a position vector v, generates like next v. And it starts with like 1 and then goes on. Okay, that's one solution. More ideas, so like a next position.
Maybe let's repeat this learned vector of 10 embeddings for as many times as we need for given sequence. So for 11th token, we will use first.
So that will, of course, work here because it's parity. But it's a little bit, again, going into, we're kind of encoding the fact that it's cyclic in the solution, right? We're kind of designing it towards the particular problem again.
How about adding a lag node, which normally blocks previous position, but slowly becomes more and more aware at every end step. It triggers swapping, so you press the state to select given position from the vector, and then again becomes invalid for n-1 steps.
So one thing I want to teach you is, it seems like the way you're thinking is I have a problem, I need to solve it. That's how programmers think. That's totally the wrong way of thinking for deep learning. In deep learning, you're not devising a network to solve a particular problem. You're devising a network to solve all problems. So don't think like this problem needs parity, this problem needs sorting, this problem, let's do a mask that will do this because we see that it's necessary. It should not be about what you see in this problem. It's more about like what computational mechanism would give you the ability to solve this always. You know, like programming languages, you can write any program in C, right? It can be parity, it can be loops, it can be whatever. You don't need, like in Python, you don't need a parity operator because you can program it on your own. Try thinking like this, and the neural network should be like a programming system. It will learn the right thing. You just need to give it the ability. Yes?
You want to use convolution or just pure vanilla recurrent neural network? Won't it learn the parity in its hidden state?
Yes.
So we can just use recurrent neural network.
Yes, so one suggestion is, since this is a sequence, and we only care about positions because the inputs will be taken care of in the other thing, how about we just have an RNN going like this, devising the next state embedding, which is kind of the same as saying this, right? It's the next state. So yes, we should try this. We should implement a network that just generates the next state over these things. So it gives it the general idea of recurrence, right? Go recurrently in time, generate something. It can be parity, but if it needed anything else, it would also do it, right? It's just a generic counting mechanism. So that sounds like a very generic thing to do. What else could we do? So yeah, okay, let's try this then. Let's try just doing an RNN. How would we make an RNN that goes on positions in TensorFlow? So how do we do recurrence at all? So there is this very, very useful link, well, which might, oh yeah, it works. It's the API of TensorFlow. It has the list of all functions, all operations in TensorFlow. So if you want an operation for something, it's probably here. So as I said, the one function that we'll definitely be using is scan. So tfscan is one of the more convenient ways of writing loops in TensorFlow. Do you know scan in like functional languages?
It's like fold?
It's like fold, except it gives you output at every step. So here is an example, and I think maybe the example is easiest to the easiest way to see. If you have an array 1, 2, 3, 4, 5, 6, right? And then you scan has an accumulator and x, which is the element of this array at time t. And well, this function just adds up. So if you scan a function, it will, like it starts, you can give it an initializer, which is the first element. If you don't, it starts with the first element. And then the second element is the sum of the first and the second. The third is the sum up to the 3. The fourth is the sum, and so on. Okay, so this is like you have any function, and you just apply it step by step by step by step. So what would be the plan? We will start with some initializer vector, say a learnable vector. So we'll get variable of shape hidden size. That will be our initializer. And then we will run the scan of a function that produces the next state. So we want the next state if this is our accumulator. And what is the x? The x should be our position. So we need a function that just gives us positions in a certain range. But we will not use the x, right? So the function will take an accumulator, will take a position, but we're ignoring it, right? Because we want to be generic. And what will it return? Well, we want to return some matrix time A. Yeah, actually just a dense layer. Again, returning something of the size hidden size. Right? So this one step change would be just a dense layer. And we'll push it through all our inputs, so it will iterate and give us the result. Yeah, is that the idea? So the scan function, it's a recurrent network constructing function. So it only applies this once and then repeats exactly the same thing n times. So it will reuse the thing. It will not create a new variable.
I was wondering,
Well, so this accumulator, right? We will start with this learned thing. And in the first step, we will apply this lambda once. In the second position, we will apply this lambda twice. So we need a function to apply once or twice or 3 times.
Yeah, if we are applying a function, then we are calling this function in Python, right? And if we call a function in Python, and in this function we have this length layer, then we are creating a new dense layer.
No. So tfscan is a function that takes a graph constructing lambda, and it actually adds a cycle to the graph. So in the TensorFlow graph, we have a subgraph. That's the function. That's the lambda, right? It has an input and an output. And what a scan does, in simplification, is it creates a loop in the graph. So the Python function is only called once, while the loop is actually only in the execution of the graph. So if you add a print to the Python function, that's this lambda, it will only be printed out once. It's never called multiple times. Okay, more questions? Yeah, so let's go. I hope you can try. Connect. Try to write the scan thing instead of the positions, right? So what I mean is, let's replace these 2 lines by a scan of a lambda of this sort. And, well, let's then see if it works. Let's see if it trains. So we have this doc under this link. There is a doc to share results, so I hope you'll make it work, and then we can share the code and see, see who made it work well. Mm-hmm.
But for this, we don't need any of this fancy RNN cell, TensorFlow.
No, just scan.
It's forbidden.
It's forbidden. No, actually, you don't need any of this fancy RNN cell stuff ever anymore, because tfscan took over almost all of the functionality.
There was a link.
Oh, yes, sorry. There are.
I actually have a high-level question.
Uh-huh.
When we introduced the positions to the previous code that we simply uncommented the lines,
Mm-hmm.
our accuracy was 100%,
Yes.
after 80 steps. So what kind of results should we
Well, so, okay.
be waiting for?
So if for the eval set,
Yeah.
we had the same length as the training set, right? It was both
Okay.
10.
Yeah.
If we did the length for the eval set, you should try it.
Okay.
For the evaluation generator, change the length to 12. So first of all, the graph would not build because it's reshaping to 10 and its length 12. It would throw an error. But even if we made it work, the embeddings, it would not generalize, because this would be this variable for the 12th position that was never ever trained, right? It has no chance to generalize. While we want something that would really generalize to a higher length than what we were training on. Which link should I? Is that okay?
There's a question?
There was a question about links. So there. Oh, sorry. Yes.
So in general, if say I want to write some custom, I don't know, some neural Turing machine or something like this, you would in TensorFlow, you would advise using scan?
Scan. Yes.
Okay.
Scan is a very good. So there is a new mode in TensorFlow which is called the eager mode. It's a dynamic graph mode, and then you can just use for, the Python for, and it will convert it. But it has, yeah, it's not mature yet. So I use scan for now, but the for is even more convenient sometimes.
Can you then transform this dynamic graph into a static one? Not really?
Depends what you mean by transform.
Yes,
Not in a single one, right? Because it's dynamic. It's different for every time step.
yes, of course. But if I accumulate this computation using for loops, as you said,
That's what it
I
does.
end up with
Yes.
a graph, right? A dynamic, but still a graph. So can I transform it into a static one? Has all of this computation?
Well, it's what it does in the back, right? The eager mode. It runs the Python thing. It gets a graph, then it executes it. And then on a different example, it will be a different graph. So the problem is every time you run it, it's a different graph.
So can I still serialize it and launch it on multiple machines and do all of the stuff I can do with static graphs?
You will not run the same graph on different machines because it's a different example. The graph depends on the data now. That's why it's dynamic. So it's a different graph on a.
Can I first run this, construct this dynamic graph on a specific example?
No, you cannot because it's different for every example. That's why it's dynamic. So you cannot construct it once for a different example.
Yes,
Right?
but
So-
what if all of those examples have the same?
But that's the point of dynamic things you don't know. So there is no one graph. There is a function that, given an example, constructs a graph. And that can run on multiple machines.
Yeah, of course, but I mean, this is not the only advantage of dynamic graphs, right? As you said yesterday, we also have more debugging capabilities with dynamic graphs, right? So what I'm asking is, like, let's forget all of the recurrence and all of the variable input stuff. Let's say that we have a feed-forward neural network. So then, can I construct a dynamic graph using TensorFlow eager mode, and then transform this graph into a static one?
No. But you can have the same code that will run in eager mode, and you use that for debugging, and then you just turn off eager and run the same code in static mode.
So the code will be exactly the same. Just
Yes.
in eager mode. Okay.
Yes. Yes, that you can do, but not extract from the code. Yeah. But for now, let's focus on scan. So TF scan. Let me go again to the doc. It gets some function and some elements. And what's important is to check which axis of the elements it will scan over, right? So the elements are a multi-dimensional tensor. And you need to keep in mind which of the dimensions is the time one, right? So we had batch by length by 1 by something, right? So it's very important to check what format does this function expect. Right. So for reasons related to implementation, this expects time to be dimension 0. While we had batch on dimension 0, which is the convention. So before calling scan, and that's one reason why the dynamic RNN exists, by the way, you need to transpose your inputs to make sure that time is on dimension 0. So one function that you will definitely need is tf.transpose. So if you have a two-dimensional tensor and you want to just swap dimensions 0 and 1, you do something like this. If you have a more dimensional tensor, then you can swap you give the new list of dimensions.
But like here So like for this, we actually don't need to pass the real values, like the.
Oh yes, you don't need to pass
Pass
x.
something of its shape, right?
Yes, so instead of tf transpose, you could just use, there is another function that's called tf range. And since our length is 10, you could just use that one instead of the x. It's just if you happened to pass x, you need to be very careful that the scan treats the 0th axis as time. So what you get passed to the A here is actually the tensor of the shape that as if you removed the 0th dimension. Everything else gets passed. Okay, and I think this is a good example, like when you actually write models. So a lot of things that you need to focus on is controlling that you're actually understanding which dimension is what and whether you're changing them in the right order. And yeah. But these are, don't hesitate to tell and ask if you have something running and you're wondering, or, or something not running and you're wondering why. Let's tell everyone so we, so we see what the problems are and how to overcome them.
Sorry, if we transpose, we need to transpose back after the scan.
Yes. Or, so if you do it like with the, just with the range, right, you have your position embeddings, you can make the batch size 1. So when you're adding tensors, normally to add two tensors, it's pointwise, so they have to be the same size, right, the exactly same shape. But if one of the dimensions is 1, the tensor will be broadcast. So for example, if you have a constant, which has just shape 1, and you add it to a tensor, it's the same as adding the same constant on every dimension. It's called broadcasting. So if you have a tensor, of size like batch x, y, n, and you add a tensor of size 1, whatever, x11, or say n, this will work, right? This will just add, no matter what this is and no matter what this is, it will broadcast. It will add the same things on all these other dimensions. Is that clear? So if you generate something that has like 10 by n, and you want to add it to the element on every batch, you can just make this dimension 1 with the reshape.
I got it working.
Okay. Okay. So there are different ways to make it work. So someone was just putting, just copy paste the code with the scan here. So there was someone who made the scan with the inputs. So it's interesting to have just the positions, but also the positions and the inputs together, in which case we might not need the conf layer. So we should try all three possibilities. So there is like one solution is here. So in this solution, we take the inputs x, transpose them. So we'll be doing a scan over this transposed x. And in the scan, we use the state, the accumulator, and the x, and we just add it. So we put a linear layer over x, a linear layer over the accumulator, and add them. So this is actually like an RNN, right? we don't have any convolution here anymore. So this is an interesting thing. Like the convolution is like just for the outputs, but it's a 1 by 1. We don't have the 3 by 1 convolution anymore. So it's not just adding position, it's a full RNN, a specific kind of RNN. It's WX plus W state. This is actually an interesting kind of RNN. I will tell a word about it in a moment. But did someone have a different solution, like just using positions? So one thing to note, if we didn't use the X here, like if we remove this part, right, then it would be really only an information about positions, but then without the 3 by 1 convolution, it should not work because it doesn't have the access to the input, right?
On the second page, there is a solution.
Oh, on the second page, there is another solution. Okay. Oh, so now we do a scan of positions over the transposed inputs. Okay. And we transpose them back, then concatenate. Does this work? Who run this? Okay. Was the accuracy 1? Okay, perfect. Any other solutions?
I should maybe mention that the one I put out, like the previous version, was without the positions, like whatsoever. I mean, it worked without, like.
Yes, because it is an RNN, so it has the, yes. But if you remove the X, if you just had the A's, then it wouldn't work, right?
I checked before without positions and it didn't work, but I'll check with the positions.
Okay, so one thing I would like you to update now is, so I changed the problem setting for sequence models to have, so the generator now takes the length, and it generates things of size L. And then I will use the generator of length 10 for training and 20 for eval, okay? So now I'm making the problem harder. Okay, previously we had the same length, 10 and 10 for training and for evaluation. Now we are having 10 for training and 20 for evaluation, so it's getting harder. So after this change, I need to be a little bit careful, so I need to change the shapes. This was 10 before. Now it needs to be none. None is like if the tensor shape will be changing, then you say none. And also in the reshapes here, that was 10. When you're reshaping, you can allow to write -1 on a single position, and then it just puts as much as is left there. Okay, so the things I changed is I put none here and -1 here. And then, of course, I had to remove these positions because now if I uncomment this, then it will fail when it runs on the size 20 because it will not be able to add this variable, right? So I had to remove this, but now we have a new solution. So let me try this. Okay, that looks quite good, I would say. Okay, so it seems like we're quite good with this task.
Can you show us the code?
Mm-hmm.
The model.
Yeah. This one.
Yeah, with the generators. So a bit higher.
Mm-hmm.
Yeah, thank you.
So the generator is just the only thing that changes, like.
Yeah, but I don't know how to use it because I'm getting in. Oh, okay, I see. Yeah, thank you. I forgot what I'm done.
Yeah, it needs to be a function to pass it later to here, right? So this way of doing positions seems to work. Now, if this task was to look like 3 things back, 3 positions back instead of just 1 before, then the 3x1 convolution would have a problem again, right? Because we only had 1 layer. The RNN you proposed would solve it in the sense because it could accumulate 3 positions back, but it would have the problems on more complicated tasks which require more than a constant memory, as we talked in the morning. So I want to just tell you 2 things before the break. One is that the TF scan you have here, so we used it to scan over the input, right? 1, 2, 3, 4, 5, 6, right? To go, the scan went in this axis, right? But you could use the scan, you could just create a range and use the scan to construct like a neural GPU to go in this axis and have a convolution in every step. Okay, so TF scan allows you to do recurrence on any dimension you prefer. The other thing which is really important to note is, like for example in this version, inside the scan, so this is something akin to an RNN, right? In every step of the loop, you have a dense layer. Now, when the networks get bigger, like our networks are of size 32, but people train 1,000 or 8,000. So this becomes a big matrix multiplication. Because if this size is 1,000, then it's 1,000 by 1,000 matrix. It's 1,000,000 elements, 1,000,000 floating point multiplies, and they happen in every step of the loop. And the scary part is, because the loop, like the accumulator, comes from the previous time step, it needs to wait for the previous step to accumulate. So it has this big matrix multiply, but it needs to first happen in step 1, second happen in step 2. It's not parallel. But things like this, TF layer dense, this doesn't depend on the accumulator. This only depends on the X. So you could actually do this in parallel for all time steps, once and for all. Right? You could write this TF layer dense outside of the scan and pass it to the scan after the multiplication. And if the network is large, that would speed you up possibly by a factor of 10 times. Because the big matrix multiply of this one big tensor with time dimension, it would be spread over different CUDA cores on your GPU or spread over TPU cores, and it would happen very fast, while this will happen step by step. Yes, question?
Dumb question. Once it's removed, this first part, TF layers dense X, this fails, right?
This will not work, yes, because it...
Check it here. It's 0.6. And you say that I can feed it, so where it would go if I feed it from the outside?
If you go from the outside, you would make a 3x1 convolution after that.
Once again, I would add a dense layer after that? Or?
A 3x1 convolution, because you want to look at this one position to the left.
I see. So you're suggesting just to remove this X32 and put instead...
Well, this is what we put in this other solution, right?
Okay, I miss it.
Like here, right? Here we have the positions. We just have the layers dense. We ignore the Z, right? It doesn't come up here. And then we just add it to the X.
Yeah.
But we have the 3x1 convolution here. That's why it works. Okay. Yeah, I think, this is just an exercise to give you some feelings for sequence models. As I say, the really good sequence model would have a recurrence not just on this axis, but on the whole thing. So you understand that the things I'm talking about have been implemented. And for example, they're part of the tensor-to-tensor library. So, so you can just go to the link there, and there is the like an architecture that's similar to neural GPU with a scan, and you can take a look at that. So yeah, I think so. You can try the task with when you're repeating not the previous digit, but like 1 minus before or 2. You can see that it will not work with the convolution. It should work with the RNN with your solution. A lot of things you can try, but I think it's time for us to think of a break. If you have questions, please come. And after that, we will move to models that are not deterministic. So we will think about problems where this does not solve them. And I'll show you why it doesn't and what's the solution for that. But that will come after the break. So thank you. And if you have questions, please ask.